Hello, everyone. I'm very excited to be here today to present this technical deep dive about testing infrastructure code with a special emphasis on TFTest. I hope you're going to enjoy it. So let me introduce myself. My name is Sergei Bulavintsev. I'm a DevOps engineer here at GlobalDots for almost a year now, with more than 15 years of experience in IT. I was working on multiple cloud migration projects, successfully migrating infrastructure and applications to the cloud. I have a certified Kubernetes administrator, developer, and security specialist certifications under my belt. A bit about GlobalDots. We are a 20-year global leader in cloud innovation, connecting over 1,000 global businesses with the latest cloud and web technologies, such as security, web performance, DevOps, and cloud management, cloud migration, corporate IT, and also advanced AML models. Okay, enough about it. Let's start to talk about tech. This presentation will be split into three parts. In the first part, I will tell you why you need to test your infrastructure code. Second part will cover tests and how they maps to infrastructure code. And finally, I will tell you about TFTest, what it is and how we can use it. So let's start. Infrastructure as a code can be defined in many different ways, like CloudFormation, IRM templates, etc. But I think that most of you use Terraform to describe your code. This is the basic example of Terraform resource defining EC2 instance. Well, imagine you receive pull request adding this resource. It seems totally legit, right? And maybe you even run the Terraform plan to ensure that this resource is working as expected. The plan can provide you with, a lot of useful information, like if you have your provider correctly configured, the syntax for the resource is correct, and that the amount of resources created is exactly what you'd like them to be. But even successful plan fails. In this example, you can see that while the resource itself was created correctly, was correct, the AMI value for the resource wasn't. We can prevent such errors and many other errors if we test our infrastructure code. There is, nothing worse than running Terraform apply of some kind of complicated project for a long time, maybe hours, only to find out that in the middle of the pipeline something fails. When it happens, you're one-on-one with half-formed infrastructure, which can be ridiculously difficult to fix. I'm not even saying that about all the time that you have to spend to find the issue, fix it, and then rerun your pipeline. And then the pipeline can fail again. So how we can address it with tests? So let's start with the basics, test basics. Since infrastructure code is basically just the code, we can and we will use the same concepts as developers use to test their code. I'd like to provide you with a little bit of theory. So test environment, what it is. Introduced by Mike Cohn in his book, Succeeded with Agile in 2009, the test environment is some kind of meta thinking about testing in software. Test environment will help organize developers their strategy on how to implement testing. As you can see at the bottom of the pyramid, there are small, simple tests, which are usually pretty fast and, they can provide rapid feedback. On the top of the pyramid comes the complex integration test, which can take hours or even days, I don't know, to complete. Pyramid also reflect the amount of tests you should have in your pocket. So you should have like a lot of small tests, which are pretty cheap ones, fewer integration chips, like which costs medium amount of time and effort to put into, and maybe a small amount of end-to-end test. Now, let's take a look at how the pyramid stages works in detail and how they maps to Terraform tools. And the first one, which I'd like to start with, is Linting. Linting is basically just validating source code to make sure that it is compliant with the code standards. I think that everyone faced failed Terraform plan or apply due to some kind of, I don't know, missing commas or missing parentheses, something like that. So which tools we can use for linting? Two most common ones, in my opinion, are the Terraform FMT and TF-lint. Terraform FMT is obviously built into the Terraform CLI. It allows you to check and rewrite your Terraform configuration to a canonical format and style, which makes it easier to read. TF-lint is an open source project for Terraform, and it allows you to catch common errors, warn about deprecated syntax, and enforce best practices. Another type of tests at the bottom of the testing pyramid, so the cheap ones, is static analysis tools like security scanning. Those tools will analyze the code and will look for some common security mistakes. For example, publicly, available S3 buckets or passwords hard-coded in the code. So, yeah. What are examples? Snyk and TFSec. TFSec are examples of such static analysis tools. Snyk it's much more. It's a whole platform that allows you to test code, just code, infrastructure code, containers, maybe even cloud resources. And Snyk has both, free version, enterprise version, and several plans according to your use. TFSec on its site is a totally open source tool developed by Aqua Security, and it only supports Terraform, but it uses static analysis of your Terraform code to spot potential, misconfigurations. It's really powerful, and it comes with hundreds and hundreds of built-in rules. It has also has a pretty cool GitHub Actions. So those of you who are familiar with Serif action, you know that it can, run the static analysis and upload results to the security page of the repository, security alerts page. So you can always be aware of active security alerts. Unit tests. So unit test is a type of automated test that checks small isolated unit of code. Unit test ideal for validating inputs, ensuring that your cloud resources are created correctly. If previous tools, which I have described, provide you with everything that you need to lint or to analyze your code, obviously, you will have to write your unit test by yourself. In Terraform, we can use modules as a unit for testing. So, because it's kind of group of resources implementing one logical things like AWS API gateway stages, or maybe corresponding YAML roles. That's all can be part of the same Terraform model. There are a few testing frameworks which which can help you with testing your models or Terraform code, like TerraTest and TFTest. I will cover them later. Now, the final type of tests are integration tests. This is pretty expensive and complex type of tests. They allow you to test how different parts of the system are integrated with each other. Imagine that we have a Terraform module for EKS cluster, and that we also have a Terraform module that install Helm charts into it. We can test how they integrate with each other. Can we pass values from one module into another? Is there a dependency issues? Maybe sometimes a Terraform will try to create resources in the wrong order. Maybe you want using the pinned version of the Helm chart and now it's incompatible with your version of EKS cluster. So that's totally possible. And finally, the most complex ones, they're functional or also known as end-to-end tests. What it means is that you can have to create the whole project consisting of multiple, maybe Terraform models, test that your system is working as expected, and only then you can clean up the resources. So end-to-end tests, they may involve running different tests than Terraform tests, like sending API request to provisioned API gateway, checking that specific entry was added to the database, or anything else that basically is required by the logic of your project. End-to-end tests, since they're slow and more expensive, they usually take a lot of time to complete. So probably you don't want to trigger them on each pull request. End-to-end tests are good candidates for a nightly run. So if you don't want to be afraid of deploy Fridays, and if you want to make sure that your code is working properly before applying it to production, make sure that you test your code. And just don't stick with just one type of tests, use them all. Because having all your tests pass successfully ensures that your infrastructure is stable, and stable infrastructure ensures your good sleep. Now let's take a look at a few test examples. So give me a second. Okay. Remember that AMI issue from the beginning of my presentation. TF-lint can spot and highlight such issues with ease. In this specific case, we were using invalid AMI ID, and it is highlighted by the TF-lint. In this example, TFSec, the security tool, highlights a possible security issue. So AWS load balancer is using plain HTTP instead of HTTPS. Of course, if that's your intention, you can lower the severity of the issue from the critical to warning, or maybe even silence this error. However, I would argue against changing the defaults, because usually those defaults are best practice provided by the security experts. And another example show us the TFTest output. In this test, AWS SQS Terraform model with default values should have content-based deduplication enabled, but during the test we receive false value. Notice that TFTest does a great job at showing us such things as the system state, so the version of Python, pytest, etc., which plugins you have installed, the root directory, or the also known as the directory of from where the test was executed, and the number of the tests discovered. I will get into details later about pytest and TFTest. So we have come to the most interesting part of this presentation, Terraform testing frameworks. And I'd like to start with a brief overview of existing frameworks. TerraTest. TerraTest is a Go library developed by Gruntwork that helps you create and automate your test for your infrastructure as a code. I think right now it's the most popular and stable testing framework. It requires a solid knowledge of Go language to write tests, in my experience, in my opinion. So Kitchen Terraform is a set of test kitchen plugins for testing Terraform configurations. It's using in spec as testing framework, and it's written in Ruby. And finally, the TFTest. It's the youngest among the three, developed by the Google platform team. However, it's not an official Google project. It's based on the PyTest framework, and it is written in Python. Among its advantages are simplicity, ease of reading and writing test. It also uses single assert function instead of multiple assert true or assert equal functions. Since you ever written tests in Go or Ruby, I think you understand what I'm talking about. You know, TFTest, despite its being simple, it supports such things as function decorators, test markers, parameterization, many more. It's also modular, meaning that you can add plugins, for example, to generate markdown report with test results, test coverage, or you can even create the plugin for yourself. In general, comparing the test frameworks, I would say pick the framework based on the language your team is using and you're most familiar with. For us on my project, the decision was simple. So everyone is using and knows Python. So for us, the decision was really simple. Now, a few words about PyTest. If you have ever written a unit test for your Python code before, then you may have used Python's built-in unit test module. Unit tests provide a solid base on which to build your test suite, but it has a few shortcomings. So why you might and maybe should even should choose PyTest over unit tests? So less boilerplate. You don't have to deal with any imports or classes. All you need is to do is to include a function with the test prefix, because you can use the assert keyword. As I already mentioned, you don't need to learn or remember all those different self.assert methods in unit test either. Nicer output. Well, I already covered it briefly, but worth mentioning that PyTest easily allows you to tune the verbosity of the test. You can silence the test and see just dots and Fs for failed test, or you can dig deep for debug level. Also, it's easier to manage state and dependencies. So there are such things as fixtures. I will explain them later. It leads you toward the explicit dependency declarations, whatever that means. But we will get into this later. I already mentioned, but PyTest allows test parameterization. That means that it can eliminate the code duplication by allowing you to pass a set of parameters inside the test function. And finally, I wanted to mention that it has a plugin-based architecture. So you can easily extend your solution by adding plugin. And there are a lot of plugins already implemented by the community. So, as I already mentioned, TFTest is basically a plugin for the PyTest testing framework. Under the hood, it works by wrapping Terraform executable and exposing convenience methods to set up fixtures, execute Terraform commands, and to parse the output. Initially, it was developed for the Cloud Foundation Fabric repository. which is basically a repository containing blueprints and modules for Google Cloud. This repository contains a whole set of tests which you can use for reference when you're developing your own modules. TFTest allows you to write lightweight tests. These tests are basically using Terraform init and plan and don't create actual resources, or fully fledged tests actually creating resources inside your cloud provider. So TFTest can also clean up resources after the test, or you can maybe leave them for manual investigation or for developers to play around with. Using TFTest as some kind of automation. And then after developers did their investigation, you can have maybe some kind of cron job to do the cleanup. Okay. So here is an example of such fully fledged test. In this example, we have two functions. Our first function is output, and the second function is test apply. So output function takes one argument as an input, fixtures dir. So this is where your Terraform resources will be located. The setup method prepares a new Terraform environment for testing the module specified at the init time, and this function at the end returns the init output. Apply actually runs the Terraform apply under the hood and destroys all the resources. Notice that in pytest, the actual test function must start or end with the word test. Also notice the word pytest fixture. So what is a fixture? It is a helper function that I use to prepare everything for the test. It can be applying Terraform resources, mocking AWS entry points, or maybe populating database with test data. So basically, it's steps plus data. So, and the function that did those things are called fixtures. Now, a little bit more theory. So the arrange, act, and assert pattern is a way to structure your test so that they are easy to read and understand. This pattern is also known as the given, when, and then. The order is important, so don't be confused with act, assert, arrange, or act, arrange, assert. So the 3 steps to 3 A's. First one is arrange. Arrange is to set up the conditions for a test. This might involve creating objects, setting variables, or anything else that's required for a test. Act is where you actually execute the code for your test. And assert is a step where you verify the code that you're testing, that it behaves as expected. This might involve checking the value of the variable, or maybe, verify that the certain method was called. Now, how does it match to TFTest? On arrange, TFTest does Terraform init and prepares Terraform modules we're about to test, cloud provider connections, so etc. On act, it runs Terraform plan or apply and parse this output as JSON. On assert, it validates the received result against the expected outcome. And on clean, it cleans up the resources. Now, let's take a look at more TFTest examples. This is a simple AWS SQS Terraform module where we define some of the values and some values are defined by the model's defaults. After applying our test, we receive the JSON with the results. This is an example output of the TFTest internal structure, output structure. As you can see, it's pretty complicated nested list of digs. So to write a test, first you have to parse it. Every dict inside the list represents a Terraform module, and it has its own address. So important thing to notice here is that by default, pytest captures all output, including print statements. So to debug variables in pytest, you have to disable pytest capture. This is an argument to the CLI pytest. I will maybe show it later. Next, this is an example of pytest fixture. It does, we already saw one, and this fixture does all the test preparation by calling the function plan runner. And this function on its own can be placed inside the conf-test.py. It can be placed inside the root of the project, and it will be available to all tests in the project. Also worth mentioning fixture scope. So it affects the fixtures lifecycle, and by default, it will be invoked once per function. So for us, it means that with the default scope function, for each test function, TFTest will run the Terraform init, then it will run plan or apply, which we probably don't want. If you have a couple tests, on every test, Terraform will do all the steps like init, apply, etc., etc. With the session test scope, Terraform apply will run only on the beginning of the test session. Then all your tests can be executed, and only then the fixture will be deleted. Now, what can you test inside your Terraform code? Well, you can start with the amount of the created resources. In this example, we check that our Terraform module creates 2 resources. Maybe you want to dig a bit deeper and check the amount of created resources per type. So this is an example. We have 5 resources, and we want to make sure that we receive desired amount of each resource, and no less, no more. And of course, you can test any attribute of the resource by comparing the resource of the test with the expected value. So here I test resource attributes one by one, but you can compare the whole JSONs if that suits you better, like in this example. So it also shows you that you can pass different variables into the Terraform model. So first, I define, on this example, I define variables as JSON in multi-line string, and then I pass it as an argument inside the plan runner function. This test actually contains a catch. It tries to test ephemeral storage size, and it will never succeed with the plan runner fixture. State of some of the resources are only known after apply. So, just be aware of that and use the proper type of test. So it will work with the Terraform apply, with the apply fixture. Installation of test. It's really, really simple. You can use pip. You need to install the pytest, which is a core framework, and the TFTest, which is a plugin for the pytest. Of course, most likely you will want to use Python virtual environment for that. There are many ways how you can run your tests. You can run a specific test. You can run a module like a file, or you can run the whole directory. Pytest is really flexible in approaches and selecting the tests which you would like to. It even provides you some kind of simple queries where you can precisely select tests which you'd like to run. So how we have implemented it for our project for testing Terraform models. We are using self-hosted GitHub runners to run our tests, which only have read-only permissions to AWS infrastructure. So far, we only run tests against the Terraform plan. So those tests are really, really lightweight, and they basically don't cost us anything. But at the same time, they provide us with a good amount of information what was changed and if our modules is working as expected. We run our tests on pull requests on each changed Terraform model. So with some CI magic, this is an actual screenshot from our pull request. When a new pull request is created, the pipeline generates a list of changed models. Every changed module is linted, formatted, and checked by the TFSec, and of course, tested by the TFTest in parallel GitHub runner. For every changed module, a separate message in the pull request is created. Another cool thing that is that I update every message in the pull request on a test workflow rerun. So this keeps the pull request clean, and it prevents pull requests from dozens of similar commits. You may ask, did all those testings paid off? And I think yes, we actually found a few really shady bugs related to provider version update. And it also forces everyone in the team to follow the same formatting and style, and which in its own way making code more readable and maintainable. It also, of course, ensures that we don't make any security flaws. And overall, I think that it's making reviewing of the pull requests a nice and simple process. So a few tips on creating your tests. Test various configurations with your model. For example, by providing different values, TFTest can provides you with multiple ways to do this. You can use parameterization. It will be really easy to provide multiple sets of different values inside the model. Try to keep things simple. Remember that simplicity in many ways means maintainability. You don't want to be in the situation when you're the only person inside your team who understands your tests and you're the only one who actually using them. Parallelization can speed things up. When your code base grows, it makes sense to run tests in parallel, especially for complex integration tests. Tests are code, so link them to use the same principles to work with them. Use the style guide, format them, link them, etc., etc. Now, areas of improvement. For our project, as I already mentioned, we test just the Terraform models, and we have some plans on running tests against the actual projects. Of course, this will cost us money, but it will make our sleep much, much better. Run end-to-end tests. Since we want to run end-to-end tests, we want to actually create resource in AWS, and that means that we will have to give permissions to the TFTest, which might be a concern from the security perspective. Another interesting project which we would like to integrate into our pipelines is InfraCost to watch AWS cost estimations in pull request. And finally, the most interesting area of improvement is integrating local stack or Moto to run API tests offline. What those project does, they provide you ability to mock API requests to the AWS, and basically you can actually create AWS resources, but they will be a virtual resources, and you can have a local stack container running inside your container. And I actually tried it, and it's really, really nice, but it has its drawbacks. Like, not all the APIs are supported. No, you can't create, not all the AWS resources are supported. And for local stack, there is a set of free API requests which you can create, and there's paid ones. So this is it, guys.